So having understood the motivation behind using the cumulative distribution function as a transformation function for transforming the pixel values of an input image to get a resultant image, because it gives a uniform distribution of the intensity values in the resultant image, we are now ready to discuss the histogram equalization algorithm for the digital images. So earlier we had assumed that the intensity values were continuous, whereas in the digital images, the intensity values are discrete. Furthermore, we assume that the distribution is positive everywhere, whereas this assumption is not going to be satisfied in the discrete case. For example, we may have an image where a particular intensity value just doesn't occur. So the assumption that P of V is not going to be 0 for the entire range of V will not hold in the discrete case. So in the earlier continuous case, we discussed that the resultant histogram is going to be uniform, and since the discrete case won't satisfy some of the assumptions, so in discrete case we will not obtain a uniform probability density function, but we would get a distribution that is much more spread out and is less concentrated on a particular intensity value. So now let's discuss the histogram equalization algorithm. So earlier we had discussed that the histogram, normalized histogram of an image I, assuming that this image has m rows and n columns. So this gives us the total number of pixels in the image as m into n. And again, without loss of generality, assume that we have a single channeled image, that is, we have a grayscale image. And we'll extend the idea of histogram equalization to the color images as well. So without loss of generality, we can begin the discussion with the grayscale images. So the normal histogram of an input image I is going to be an L-dimensional vector where L is the number of possible intensity values for any pixel in an image. So assume that the intensity values are 0 to L minus 1. And again, we can normalize these intensity values to be between 0 and 1 by just dividing each of those values by L minus 1. So the resulting normalized histogram is going to be an L-dimensional vector with each of the entries hn of vk, hn of vl, where L goes from 0 to L minus 1. So V of 0 is simply 0 over 255. V of 1 is simply 1 over 255, and so on. V of 255 is going to be 255 over 255. If L is 256, which is usually the case in an 8-bit when we are using 8-bit images. So normalized histogram is going to be L components, where each of the entry hn of v of L is simply going to be n of L over T, where n of L is simply the number of pixels having the intensity L in the input image, which we earlier discussed that we can use indicator function to raise the normalized image histogram. Simply sum over all I and j row and columns in an image, indicator function with the condition that I of I comma j is equal to v of L times 1. divided by T. So this is simply P of V of L, which is the probability of occurrence of the intensity value VL in our image I. So now to save space and for ease easing out the terms, to simplify the terms in our derivation, we'll just like represent the normalized image histogram Hn of V of L. We'll write it simply P of V of L, which is the probability of occurrence of the intensity value V of L in our input image I. So now we had seen that in the histogram equalization algorithm, we are going to use a cumulative distribution function as a transformation function. So earlier in the continuous case, we used integrals. So the integral is going to be replaced by summation, and the probability density function is going to replace by the probabilities. So now the transformation function for the histogram equation is simply T of VL is simply sum over all I equal to 0 to L P of Vi. So this is going to be our transformation function for histogram equalization, and this gives our resultant pixel value R. Furthermore, we normalized the values between 0 and 1 to get back the values back in the range 0 to L minus 1. We can just multiply this transformation function by L minus 1 into sum over all I equal to 0 to L P of V of I. And we can take the approximation and we can write it as, it means these open these open brackets denote that we are approximating this value to its nearest integer. So if the resultant value is, let's suppose, 223.6, then we will convert that value to 224, or if the value is 223.4, we can convert to 223. Or sometimes we just use a greatest integer function, or sometimes we just use a floor operation, but using the floor and ceil operation combined, that is, if the value is greater than 0.5, then we round it to the nearest nearest next integer, and the value is if the decimal value is less than 5, then we just round it to nearest smaller integer. So this is the entire histogram equalization algorithm. And note that since we are using a discrete case, the resulting distribution, so the R, the resulting intensity value, so assume that we have an image, and each of the entries in an image is going to be some pixel value. So the way the histogram equalization algorithm works is this. We will first compute the normalized histogram of an image, that is, compute P V of VL for L equal to 0 to L minus 1, where L is the number of intensity values. Second, iteratively go through each of the pixels. So each of this pixel is going to be occupying some intensity value V of L. So in the resulting image, for example, let's suppose this value is V of L, which is equal to, let's suppose, 25, then the resulting pixel value R in an image is going to be, R is going to simply sum over all I equal to 0 to 25 P of I times L minus 1 and we round it to the nearest integer. So this is the value of the transformed pixel in the resulting image. So to write this entire algorithm in one line, we can just write it as, let's assume that the resulting transformed image is Rij. There's a value of the pixel at location I comma j. So we can write it in one line simply as Rij. That is the value of the pixel in the resultant image at location I comma j is simply nearest integer of L minus 1 into sum over all L equal to 0 to I of I comma j. So this is the intensity value at location I comma j in the input image, P of L. So this is the entire histogram equalization algorithm written in one line. So the way to implement this in a computer is to first compute the normalized histogram of an image, then iteratively run perhaps two nested loop, one for rows, for rows going from 0 to m minus 1, for columns going from 0 to n minus 1, replace Rij with, for rows I, for columns j, nearest integer of L minus 1 into sum over all L equal to 0 to I of I comma j, P of L. And we have end. Return R. So this is the entire image histogram equalization pseudocode. We can write it much better, but it would depend on the language to language. So to write it more neatly, we can just summarize everything together. Step 1, compute normalized image histogram P. Step 2, for all pixels, run loop for I equal to 1 to m minus 1, for j equal to 1 to n minus 1, Rij is equal to nearest integer of L minus 1, sum over all L equal to 0 to I of I comma j, P of L. And return R. So that is the end of our discussion for the image histogram equalization.